valence shell electron pair repulsion is what VSEPR is. So VSEPR. And all it says is that electrons repel each other. Electrons repel each other, and we know that because we say negative repels negative. Electrons are attracted to positive, so positive and negative attract, negative and negative repel, positive and positive repel. So it's using the theory that these electrons, when they get near each other, they actually don't want to get near each other, and they're going to try to get as far away as possible as they can from each other. And that's how they end up forming their shapes, because they're trying to get as far away as possible. So the way we figure this out is we have to first draw the Lewis structure, and then we focus on the electron groups around the central atom. So remember the electron groups, another name for them are domains, the electron domains around the central atom. So first off, the electron groups, remember, can either be a lone pair, a single bond, a double bond, or a triple bond. These are the 4 different types of electron groups we have. And although a double bond has 2 lines, it's considered one type of electron group. A triple bond is considered one type of electron group. So we can look at a table that the book provides, and I have it on Brightspace. I have it posted on Brightspace that tells us how we figure out what the actual 3D molecular and electron geometry are. So first off, the start is you have to count the electron groups around the central atom. That's the important part. It's around the central atom. We only care about the ones around the central atom. And we have the electron geometry versus the molecular geometry. So the electron geometry is just the arrangement of the electron groups. Whereas the molecular geometry is basically the overall shape. So let's make sure you guys can see, I think you guys told me it was there yesterday, but let's just make sure you guys can see the molecular table that I've posted on Brightspace. It's under chapter 10. It looks like this. Mine printed out kind of grayish, but it looks like this. And we're basically going to use this table to determine what our geometry is going to be. And I'm going to show you how to read the table. So give me a thumbs up if you see it. It's under content, lecture worksheets, chapter 10.
Yes.
Okay, great. All right. So I'm just gonna go back through all the examples that we did, starting from the ones we did yesterday. I think the first one we started off with was the PCl3. So you guys should have this in your notes already, but I'll just go back through it. The PCl3, we drew the Lewis structure for the PCl3. We said it looks like phosphorus, 1, 2, 3, chlorine, 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 and then there was a lone pair, and these had 6 around it. This was the very first example we did yesterday. So the way we figure out the geometry of this shape is we say, okay, we're gonna count the electron groups around the central atom. And if I count the electron groups around the central atom, my central atom is phosphorus. I have 1 right here, which is a lone pair. I have 1 right here. I have 1 right here, and I have 1 right here. So total.
I'm sorry. For phosphorus, why do you put 2 on top? I'm sorry.
Well, that's just how if we go through all the steps, that's just how the Lewis structure ends up. So if you just start with some in the valence electrons and, you know, go through those 5 steps, that's what ends up happening.
Okay.
So when we have this structure, we're saying, okay, we took the time, we drew the Lewis structure out, this is what we got. I'm now just trying to figure out the actual shape of the molecule. This is just a 2D version where it says up, down, left, right. But when I figure out the shape, I look at phosphorus and then I count the electron groups around the central atom. So it's 1, 2, 3, 4. And then all I have to do is look at my table. And on my table that I have, the one I posted on Brightspace, what we're first trying to figure out is how many, the first column you guys see, it says the number of electron groups. Let me try to hold it steady. So the first column says electron groups. In this case, I said we had 4 electron groups around the central atom. So I go down to 4. So I can ignore the 2s and the 3s. So I have 3 options for 4 electron groups. In this case, the next column says how many are bonding and how many are lone pairs. So we go back to our molecule and we say, okay, we have 3 bonding, because 1, 2, 3, I have 3 bonds. And then I have 1 lone pair. So I look at the row that says 3 bonding. So I have 4 electron groups. In this case, 3 of them are bonding. 1 of them is a lone pair. So I say the electron geometry is tetrahedral. The angle between the central atom and the other atoms is 109.5 degrees. And the overall shape of the molecule is trigonal pyramidal. So essentially, if I draw the Lewis structure correctly, I should be able to just look at this table and read it across to figure out the overall shape of my molecule. Trigonal pyramidal, so I'm going to say that this means it's tetrahedral, and then it's trigonal pyramidal. And all that really means is that it's like a triangular pyramid. So we think of a pyramid like this, but instead of having a square base, it's going to have a triangular base. In reality, it's saying that this is my phosphorus and these are my chlorines. And this is what the shape of the molecule looks like. So in the book, it'll draw it out for you like this. And that's really what the molecule looks like, not like this. And we can do this for all the shapes that we went through. Let's see. Let's go through all the ones that I gave you as examples. What was the next one I gave? yesterday. I think it was water. Water was the next one that I gave. So let's do water. We already drew the structure for water. We say water looks like we're going to put our oxygen in the middle. When we draw the 2D structure, we said it looks like this. All right, so when we're trying to figure out the overall shape, the real molecular shape, we have to go to the central atom. The central atom is oxygen, and count the electron groups around oxygen. So you guys tell me, how many electron groups are around the oxygen?
4.
4. 1, 2, 3, 4. How many are bonding? How many are lone pair?
2 bonding, 2 lone pair.
2 bond, 2 lone pair. Do we all see this? All right, so then we just simply go to the table. We go back to the table and we say, okay, we got to go to 4 again. So there's 3 options for 4. We just got to find the option that says 2 and 2. We see this last option says 2 and 2. So that means that it's still tetrahedral, because anytime that I have 4 electron groups around the center atom, my electron geometry is going to be tetrahedral. Now, once again, it's saying my angles are 109.5, but this time my overall shape is bent. So what that means is, what it really looks like is oxygen is in the middle and it's bent like this with the hydrogens. And in the book, I think it just draws it like this. And this is called, we can say this is still tetrahedral, but this time it's tetrahedral bent. Okay.
When you have like double bonds. Oh no, no, I got it.
Okay, I'm gonna do the examples because we had some double bonds. Let me quickly, I'm trying to go through all the ones I gave you for examples. So all right, the next one we did yesterday was nitrogen gas. N2, we said it looks like this, N triple bond, N, and then a lone pair, lone pair. Now in this case, we still have to look at the central atom, but in our case, they're both nitrogens. There's not like a real central atom, so it doesn't matter. Anytime, I'm just gonna put a star next to this, anytime you only have 2 atoms, the only connection that they can make to each other is a straight line, meaning you can't make another shape out of these 2 atoms. You can't draw like a pyramid or any type of bent thing. The only connection that they have to each other is a straight line. So we say it's automatically linear because there's only 2 atoms. Anytime you only have 2 atoms, it's automatically linear. So meaning the only connection they're going to be able to make to each other looks like this. But let's do another linear one. All right, so let me get some more paper. If I keep going, the next shape, we started today. Let's just go ahead and jump to carbon dioxide just because it's linear too, and I'll show you. If we look at carbon dioxide, you guys drew out carbon dioxide for me. You said it was C double bond O like this. 1, 2, 3, 4. 1, 2, 3, 4. And we count the electron groups around the central atom. So when we're counting the electron groups around the central atom like this, Remember, a double bond means one electron group, and here's another double bond, so that's 2 electron groups. It's not 4. We don't say 1, 2, 3, 4. We're saying one double bond represents 1 electron group. So there's 2 electron groups total, and they're both bonding. So 2 bonds, 0 lone pair. And if we look at our table, that's basically the definition of linear. So anytime we have 2 electron groups, they're bonding, 0 lone pair, we go ahead and say that it's linear. It makes a straight line. That's 180 degrees. That's a straight line. So the overall shape is linear. So what this looks like is carbon in the middle, and then the oxygens on the end. And this is what our lab is going to be on tomorrow, just basically drawing these shapes out and getting their 3D molecular shape. What other one did we do today? We did F2. It's automatically going to be linear because it only has 2 atoms. We also did pH3, right? pH3 was the first one we did. And we said phosphorus, do like this. And then what, we had a lone pair. So once again, this is tetrahedral. I need to find one that's not tetrahedral to give you an example. Okay, we can do sulfur dioxide. If we do sulfur dioxide, let's just do this together, starting from scratch. We haven't done this one. So sulfur dioxide looks like this. Some of you guys would think it has a similar shape as carbon dioxide, but it does not, because sulfur and carbon are in different groups. So we have to start from the beginning where we sum the valence electrons. They're all in group 6, so 6 times 3. So it's 6 for sulfur plus 6 times 2 for oxygen. That's 18 valence electrons. I'm gonna put the sulfur in the middle, draw a single bond to each of the oxygens. Subtract 4. I have 14 left to play with. So I'm gonna say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that accounts for 12 of them, and I have 2 left to play with. Those last 2, I'm gonna put them on the sulfur. When I do that, oxygens are happy, but my sulfur is not happy. So remember, I can break a bond with either one of these oxygens. Remember, this is resonance. It doesn't matter which oxygen I pick. I break a bond and the overall structure looks like this, with a lone pair as well. And we say that this is the overall structure. When we go to count the electron groups around the central atom, we're saying 1, 2, 3. If we look at our table, we have 3 electron groups. 2 of them are bonds. 1's a lone pair. So if we look at our table, the table says 3 electron groups, 2 options for 3 electron groups. I'm gonna go with the 2 bonding, the 1 lone pair. So the 2 bonding and the 1 lone pair says it's trigonal planar. So anytime I have 3 electron groups, it's automatically gonna be trigonal planar with 120-degree angles. But this time, the overall shape is bent. So what that really means is it's bent just like water's bent, where it's like this V shape, where this is the sulfur and these are the oxygens.